Okay. So on Wednesday, we stopped roughly here into explaining how does a computer or a processor executes a certain piece of program. And we said this program for any hardware is nothing other than a sequence of zeros and ones, but the way you understand them is through the contract of the ISA, right? And we said you load your program through some sort of an input device to the memory, right? So the first step is you get loaded from an input device to the memory. Once the program resides in the memory, the processor itself, which is in the my right hand side here, you read the instructions from the memory one by one through the control. So for example, you are executing this instruction for now, which is our add instruction. Then you bring it from the memory, so you fetch it, what we call a fetch stage, as we'll see later on. And once you fetch it from the memory, you decode it to understand it. So we have a sequence of zeros and ones. How do I know whether it's an add, subtract? What are the addresses of the registers? This is done through what we call a decode stage. So fetch, you obtain something from the memory to your registers through the control path of the processor. And decode means there is a decode unit. It's basically a bunch of decoders and gates that try to understand for this sequence of bits, what do we really mean? Are we adding R1, R2, R3? Are we multiplying to other registers to the results in R10? So all of this is being decoded through a circuitry that we usually call instruction decoder, right? And in a pipeline, it's called the decode stage. Once you are able to decode your instruction, so understand this message within this stream of bits, then based on this, you send control signals. That's why it's called the control path. You send control signals to the circuitry that really executes the actual operation, right? Like the ALU, for example, right? So the control path controls the data path to simply add the content of certain, like this is the add instruction, basically the decoder, and then you enable the data path to understand this is an add, and then you bring in the two registers, add them, and put them in the destination. Then after you execute, you need to store it back to the register, and simply I'm done with one instruction. So what is going to happen next? Do you think? So I went through the full instruction execution. Then the processor will do what? Fetch the next instruction exactly. So I'm done with this add. I'm going to bring the one afterwards and do exactly the same thing, right? But what else? Again, the same. One question though is how does really this control or the processor in general knows where to find the next instruction? Does anyone know? So we say this is a sequence of instructions in the memory. Yeah. Program counter. Thank you so much. And this is something that most probably you have dealt with in the embedded courses, right? Or how did you know about that? General knowledge. Dr. Nicholas, of course, 3GQ. Okay, so that's good. So usually, this is also very important for embedded interfacing stuff because you get closer to the instructions. But the idea is that there is a very special register called program counter that keeps the address of the next instruction to be executed. But the same question still holds. How does the program counter knows the address of the next instruction? So program counter is a place for that address. How do I know that address? What do you think? Yeah, but the pointer is the program counter, right? Which is the address. So the pointer from 2SH and 2SI, you know, a pointer is nothing other than an address, right? So it's the instruction address. But how do I know, for example, once I executed the add, where to go to find the next one? Yeah, increment the, oh, good. So it's a good idea. So we are in the right path. So we're incrementing the program counter, but the question is by how much should increment it? Yeah, by 1 word. By 1 word. Yeah, this is 4 bytes, right? Who tells me that the instruction is 1 word? Because now you made an assumption that your instruction is 1 word, right? So this discussion is going exactly where I wanted to go. Basically, this whole thing is making an assumption that your instruction has a fixed width, right? Because if it's not one word, I cannot really increase the program counter by one word, right? It might be 2 words. So one word assuming 4 bytes, 32 bits, right? So here, the assumption is that the instruction is 32 bits. So once you are done executing one, you jump to the subsequent one, right? With a fixed width, right? So why it's very problematic for variable width instructions to execute. This is one problem with CISC hardware, that some instructions are variable width, and then the program counter need to do complex math to jump to the next one. But if all the time you have a fixed width instruction, 32 bits all the time, for example, then I know once I finish executing this one, I add 4, which is basically bytes, which is one word, to jump to the next one, right? So that's a good thing. But now, who tells me that the instruction is 32 bits for one word or 4 bytes? How do I know that? How does the hardware know that? Yeah.
Yes, just definitely can't go over the architecture.
Yeah. So one important aspect of that course is to demystify the terminology, right? When we say the architecture, we usually refer to the layer, the starting layer of the hardware beneath the ISA, right? So, which is this thing, that's the architecture. But the question is, how does the architecture know? When the architect architects the system to really increase the program counter by 4, why he thinks 4 is the right thing to do? Yeah.
It's specified in the ISA.
Exactly. So our contract is ISA, right? So remember that these things are coming from software, right? Like I wrote my C code, the compilers, they generate them, and then I have the binary file, then I load to the memory. So these things are already generated completely in the software layer, regardless of what is your target hardware, right? Only there is one contract that you maintain when you do this. It's regardless of your hardware details, except the fact that you assume I'm targeting a certain instruction set. So if this is, for example, a RISC MEPS instruction set, then you know that my instructions are 32-bit. And the back end of the compiler, when generates this binary file, the assembler, right? It will create 32 bits that represent this instruction, right? As we said on Wednesday, even though it's not only the weight, but also the values here, right, are dictated by the instructions. Because if you open an instruction set, and we would have a few examples here. If you open an instruction set manual, you will find that for every single instruction, you define what we call a register field that tells you the width, the different fields of every instruction, like the opcode, the destination, the register, and then also the width of every one, right? Without that contract, there is nothing you can do, either in hardware or in software, right? Because everyone will be in disagreement and nothing can interplay together nicely. This makes sense? Good. So another question here. If I do what I'm doing right now, by all the time increasing the program counter by 4, I am overlooking my program, right? Because the sequence of the program is not all the time you execute one instruction after the other, right? So there are other cases. What would be these cases? Yeah, a jump or branch. Yeah, like what are examples of one like a jump or branch instruction from the C high level? If statement is one thing. Yeah, thank you. Calling a function is another thing. Thanks. What else? Recursion, yeah, it's also another thing. Thank you. Yeah. Yeah. Go to, yeah, but go to is a little bit uncommon, but that's a very direct way of jumping. Yeah. Loops, exactly. Thank you. So loops, in fact, are the most common. Loops and conditional statements are the most common pieces of code in any real program. Like, and we will see this when we do the labs. If you take any real benchmark or any real application, you will find that it's composed of large portion of the code embedded in loops. So this is how you optimize your code, right? So loops, conditional statements, functional calls, goto, all are examples of branches and jumps. The problem with this kind of control instructions, we call them control instructions because they control the path of the program, is program counter for the next instruction is not necessarily program counter plus 4, because I'm not, for example, if this is a jump instead of being an add, well, let's not talk about assembly. This is an if statement, right? That will translate into a branch. If the condition is true, I might go to the next instruction. If the condition is false, I might just go to a completely different place. So the program counter need to know whether you bring the next instruction or the one after, I don't know, X offset, right? So branches mess with the program counter easy calculation, which is adding program counter plus 4, right? This is one thing that will benefit a lot from when we come into like how we do pipelining and how does this the control these hazards and how we resolve them. A big deal of computer architecture is also trying to resolve this corner. It's not a corner case, it's very common, but to resolve these particular branching scenarios. Good? Sense? Okay. So generally, I fetch the next instruction if I dealing with branches. Then the simplest format of operation is fetch an instruction from the memory, decode it to understand, send the selection lines to the data path. The data path will execute, and then the control will bring the next instruction from the memory, and keep doing this all the time. Good. So a third observation, if I'm doing this in that way, which is fetch one instruction, decode it, execute it, and then bring the next one, this is completely inefficient, right? Why that's the case? Okay, so we keep saying control path and data path. What is this really? So a control path is, well, as you said, it's mainly composed of decoders and gates, multiplexers that decide which, first of all, multiple things. What is the next instruction that I'm going to execute? And the input from the memory, that's simply the data that I need to bring in the fetch stage, right? And then I also need to decode that instruction to understand it, as we said. Once I decode it, I need to send signals, what we call selection lines, to the basically control the data path. Think about the ALU, for example, where you have an adder, multiplier, subtractor, shift registers, all these things. And then you enable, disable them based on the type of the instruction. If I have an add, enable the adder. If I have subtract, enable the subtractor. If I have a multiply, enable that or that, right? There are selection lines that are created by the decoder or the control path. Good. So this is what the control path is doing. With the data path, this is the one that is performing the actual operation, right? So it's the ALU itself, if you're talking about arithmetic operations, or it's the logic needed to bring something from the memory if it's a load or store instruction. So you execute the instruction, and we call them usually function units, right? Again, adder, multiplier are examples, or also there are what we call storage locations or memories. We deal with register files, we deal with caches, we deal with buffers, and we'll come into this in a separate page. In addition to the data, well, something in addition to the function unit and the storage in the data path, we need buses, right? Because go back to our example of the add instruction here. Let's say we have an animation here. Yeah, this one. So we said, okay, I realize this is an add instruction. Then I need to bring in my operands, right? This one and this one to do the addition on. So I'm adding R4 and R2, which are two registers, and storing the results in R2. Those are registers stored in the register file, right? So it's a storage. I have their address, go back and bring them. But what does it mean to bring them, right? These are bits. So they need wires to be transferred on, right? So there are buses, wires throughout the data path to bring something from the register file, to write something to the register file, to write something to the cache if it's a memory operation, right? So you need interconnect basically between the function units and the storage you have. And how to optimize this interconnect is also a big deal in computer architecture because it becomes a bottleneck, right? Especially if you have massive data to deal with. And then data path deals with the register file, but also deals with storage memory. As we said, caches. So you load data from the memory or you store data to the memory if you have a load or store operation. Okay, then the last stage is once I'm done executing all my instructions and I wrote the results back to the register file and then maybe to the memory, your program might be outputting something to an output device. Like again, think about 2SH, you did CNC out or fprintf or fopen or fread, fwrite, dealing with files or dealing with the console. Then if you want to output something, you need to deal with an output device, right?